So I think that was a good introduction. I'll skip that. So I'm here to talk to you a little bit about the Apache Ignite project, what it is, where it got started, where we are right now, and some main features, kind of try and do a quick overview, and then see what we offer in terms of Spark integration. So simply put, what is Ignite? It's a distributed memory-centric computing platform, right, with powerful processing APIs. So it's really about kind of storing your data in memory and then having the flexibility and ability to kind of manipulate and process this data in many different ways. So how did the project start? It was back in 2007 when we first created GridGain, right? So it was the first inception of the product. It was a compute grid. Now, fast-track that a couple of years later, and we decided to kind of open source the company and take that product and put it into the Apache Software Foundation and create what we have today, Apache Ignite. So we're the main contributors, as you would expect, in the Ignite project. And what's really interesting about Ignite is that it's been the second fastest project to graduate after Spark. And we can all see how successful and popular Spark is. So we're just hoping that this is gonna deliver on our side. There's a lot of contributors at the time, and that's kind of growing. There's huge development momentum. And the product, the code right now is very kind of robust and solid, since there were customers in production using this stuff a long time before we actually created Ignite. So you can check this data out on OpenHub and see the stats for yourself. It's pretty cool. Okay, so I like this view of a kind of a reference architecture diagram just to give you an understanding of what Ignite is and where it fits in. So if you think about it, Ignite at its heart, what we have is the memory-centric storage. So this is the ability to store data in a distributed way, right, in a clustered way, and having the ability to scale that linearly by adding nodes. Now, right below that, you can see there's two kind of parts. We have what we call Ignite native persistence and third-party persistence. So the Ignite memory-centric storage, as the word denotes, it's all in memory, right? So with Ignite native persistence, what we can do is have the superset of the data residing on disk. So that means I have hot data in memory when I'm using, and then cold data or old historical data can reside on the disk, right? So that's a very new implementation or feature that we've rolled out with Ignite version 2.0, which just came out about 3 months ago. So very new, very exciting, very cool stuff. In the meantime, what we always kind of offered and what was possible is have this third-party persistence. So it's very easy to integrate Ignite with an external persistence store, right? So you can actually keep your data on disk and recover from there. So you can use that for initial loading, and you can use that for kind of bringing and rehydrating the data into Ignite. Now, the interesting part, and we'll talk about how we store the data and how it's kept in memory and how we manage that. But what's more interesting is the ways we can affect and process this data, right? So we have a plethora of APIs that we can use to actually change this data. One of the main ones I try to kind of point out there that kind of stand out, we have a SQL API, full ANSI 99 compliant SQL. So you can run distributed queries with distributed joins in Ignite and bring your data together and then really ask interesting questions from your data. Then you have the classic kind of key value operations, right? So I can access my data using a key and then fetch the value and process it. It is very consistent. It is highly consistent, right? So we have what we call a transactions API, full ACID compliant transactions. So you can trust it as a single source of truth, and you can have what we call distributed transactions across tables or caches, as we call them in Ignite. And you can even wrap this transaction all the way down to third-party persistence, and also with Ignite native persistence. So we'll have guarantees for transactions that are persisted and durable before we kind of send you a return of that operation's been successful. Some other interesting stuff is we also have streaming. So there's many ways by which we can stream data into Ignite and before we start processing them. We have an early stage alpha release of some machine learning libraries, nothing compared to Spark, of course, but it's certainly something that's being worked on by the community and being progressed as we speak. And more interestingly enough, for this session, we have what we call the IgniteRDDs. So that's the way we're going to talk a little bit more about that, of how we integrate Ignite and Spark. The last bit I want to kind of point out here is what we call the compute grid. So not only can I store my data in memory, but I can actually execute code on each of these nodes. So it's a distributed kind of platform. I have a bunch of nodes that I'm running. And what I can do is send closures either to one or all these nodes to actually execute some piece of code. Now, the idea behind that is not to just read the data and process it on the client side, but have the ability to process the data as close to the source as possible. So it is a distributed system, but it's all about thinking, how do I do most of my processing locally, right? And that's the idea. And we'll talk a little bit more about that. So a couple of the terms. I mentioned memory-centric. So what is memory-centric, right? What's the difference? I mean, you can only kind of compare it to what we call a disk-centric system. So these are your traditional databases, right? They're based on disk. They're optimized for disk use. And then eventually, some of the times, you see what we call memory as a cache layer on top. So that's kind of different. It just works by caching the results. The difference with memory-centric is that it's memory first, right? And we use memory not only for storing, but actually processing the data. And what this opens up, it opens up the processing capabilities of what we call co-located processing. So what I just mentioned, processing the data as close to the source as possible and not having this client-server mode. Okay, so I've got a diagram here of kind of a traditional or a classic, let's say, Ignite deployment. We usually work with a lot of financial services customers. So it's an example of a couple of applications that you would build, like payments. So that would use a transactions API. You need to guarantee that your transactions are running. Then you have risk calculation engines, right? You need to have the ability to execute SQL queries or mathematical functions across your data to be able to do that. And a lot of the times, that's data that comes from payment applications and other applications that hold all this interesting data that you want to crunch. We can build trading platforms, right? So it's all about quick trading between systems. And usually one of the most popular APIs, I would say, is SQL, compute, and then transactions, right? Below there, you can see a cluster, right, of 3 nodes. And pretty much once you put these together, they cluster up, they create the Ignite cluster, and then you can deploy what we call caches, right? So you can have your tables, which are in memory. Now here, what's interesting, after we released what we call the Ignite native persistence, we have what we call durable memory, right? So that's the ability to not only store data in memory, but also overflow onto disk. And what happens there is we actually have the superset of the data on disk, right? And then we can load that in memory as required. So there's shared states or shared data across your applications that you can deploy. You can create multi-tenancy by segregating different cluster groups, still running within the same cluster, but separating them out. And of course, this is compatible and we can run whether in .NET, C++, or Java. So durable memory, a little bit more about that. How does it work behind the scenes? So first of all, when we're working in memory, it's all off heap. So you have predictable memory consumption, so we know exactly what's going to happen. We have automatic defragmentation, and we, of course, remove any noticeable GC pauses since we don't have to work with the garbage collector. Now, once we start persisting onto disk, we have a fully transactional write-ahead log. So any transaction that comes in is first written into the write-ahead log, right? And then if there's any loss of data or your cluster shuts down and you lose that, once you restart and you recover, now you can replay those transactions and persist them onto the disk. What this also allows, once you're working with disk, is that we have instantaneous restarts, right? We don't need to wait for the data to be loaded in memory before we have the ability to start querying it, right? So great stuff when it comes to quick recoverability. Of course, what's important there is that the query speeds and the performance won't be the same if you're working on disk, right? It's understandable. So a little bit more of a couple of other features. So there's a number of APIs you can use that I didn't mention, like a REST API that you can deploy on top. You can work with Memcache. There's an ODBC and JDBC driver, so you can plug in your Tableaus and your Pentahos, right, and do your BIs and all your kind of statistical queries, let's say. Okay. We also have service grid. So that's the ability to deploy in-memory services on each of these nodes and expose certain functions that you want to call and execute. So I did mention I want to talk a little bit about the processing style. So once we've loaded the data into memory, there's multiple ways you can structure it. We have what we call partitioned data sets, right? So we can load the data and partition it across a number of nodes, or also called sharding, right? Once we get it in there, we use what we call data locality or data affinity. So we decide where and in what node a piece of data can reside. We also have the ability to have fully replicated caches, which means that the data for a certain table will be available on all the nodes. Now, when it comes to queries, then you can have operations, SQL operations that can do local joins, right, between partition caches and replicated caches. But more importantly, when we look at it in the terms of processing, you have client-server processing, where I can read the data and process it, but also co-located processing, where I can send the computation or the change request to the data or the node that actually hosts that data. What this means is we reduce network traffic, right? There's no calls between the nodes to get the data that's required. The function goes only to the exact server that's required. And we call these distributed closures. And what's important about this is you can enable peer class loading, so you don't need to predefine or preload these classes or functions or closures onto your server before you can call them. So you can deploy a cluster, run your Ignite nodes, and then start firing the task as you write them on the client side. What's great about this is that you can actually send the request using the same key. So if I was loading the data and I was using a certain ID to load an employee that will dictate on which physical server that will end up, I can use the same thing with the compute API and direct a closure or a function to the exact server that needs to process that. So here's another example deployment, I think a bit more relevant in what we're kind of talking and doing here. So this is if you can see, I've got 3 nodes there. I've got also some Hadoop data nodes on the bottom. So what that does is we use Hadoop as the backend where we have our data and we load it into Ignite. Again, we can leverage data affinity or data locality, so we can have a one-to-one mapping between Ignite nodes and what is in memory and what's in the Hadoop nodes residing on disk, right? In that scenario, we can have many different ways where we can load the data. We have what we call Ignite Streamer. Now, we have many abstractions for that. One of them is a Kafka streamer, right? So you can plug it into your Kafka and then start reading messages, transform them, and put them into the cache. You can also use JMS streamers. There's a bunch of different integrations that you can use there. So there's ways to do initial load from a backend, right, from the Hadoop cluster, let's say, and then there's loads to kind of ways to impact or update data with different ways. Once we get it into the grid or in Ignite, you can then use the traditional APIs that you would access, right, as SQL or compute. But you can also use the IgniteRDD, which is an implementation of the Spark RDD, right? That allows you to pretty much access data that is in an Ignite cache through the RDD framework. So in that situation, what happens, if we look at a Spark application, we have the Ignite in-memory shared RDD. So that's kind of stored in memory across a number of clusters and servers, sorry. And then on top of that, we can run our Spark jobs. So what that gives us, it gives us mutability on the data sets, right? Because now it's hosted in Ignite, so I can change that data. I can use the Ignite APIs to affect and change it. But it's now visible across your Spark jobs, right? And it can be across multiple workers or across applications. So you can run an application, gather the results, write them into the cache, and then restart your application and still have the results there. What's important is that it runs on Yarn, on Mesos, on Docker, right, or on any cloud or any on-premise infrastructure you would expect. As long as it's possible to run Java, then it's possible to do that. Another thing that I didn't mention here is how we keep the data in memory and how resilient it is. So when we have partitioned data sets, we can also specify a number of backups, right? So that's basically for every key that I hold, I will have one more backup of that version. You can also specify any number of backups, right? So it doesn't have to be one-to-one. That means as you increase your number of backups, you increase your redundancy, right? So if I have a backup of 1, it means if I lose 1 server, I can still recover my data. I have 2, then I can lose any 2 given servers, right? And what is important is we also have this dynamic scaling. So we do partition the data and we put it in memory, but it's possible to actually scale. When you add a node, we don't need to have downtime or stop operations, right? The rebalancing of the data happens on the fly, so we shuffle the data around so that we spread the load across the cluster. So if a new member comes in, then some of the data leaves from the previous members and goes to the new one. Then we create backups for those data and distribute them across the other servers. Okay, so a little bit about how, just wanted to show a couple of lines of code here of how easy it is to get started and work with an IgniteRDD, right? So you just start with the Ignite context that kind of comes from the Spark context. So you pass a configuration where you can specify what your RDD is going to be, and then you can read values from that RDD, or you can save values. And another very important point here is that we can actually speed up Spark SQL, right? So one other thing I didn't mention is that once we get the data in Ignite memory, we can specify indexes, right? So that means if you have specific queries that you know will hit specific fields that you can set up indexes, then you can speed up a lot of that SQL. So we do that in Ignite world, and that falls over also into Spark. So when you're using Spark SQL, it's very easy to leverage and take advantage of that in-memory capability, right, of indexes. This is just an example of how you can convert. So right now, there's no native support for DataFrames. That's definitely on the roadmap and one of the tickets that our guys are working on. So we hopefully should see support soon on that. Just a quick rundown, I think, as a kind of slide here, just to separate and just point out the differences, I think, in Ignite. So Ignite is, first of all, fully agnostic data source. We work as perhaps a data virtualization layer where you can aggregate a lot of data sources, put them in the Ignite memory, and then use all these APIs to query them, right? It comes with a compute grid, right? So you can process that, similar to perhaps how Spark operates. Another main difference is perhaps you can see Spark more as a batch-oriented system where you can load stuff into memory and then process that, whereas in Ignite, the data is always in memory. You define upfront how you're going to partition your data, how you're going to deploy it, and how it's going to be in memory, and start operating and using your SQL queries or different APIs to affect that, right? It has the zero deployment, so we have this distributed class loader, so you don't need to load the classes to all the cluster members. We will share the classes as the cluster starts up. We have full ACID transactions, probably one of our strongest kind of points there with the technology. And of course, it's less focused on Hadoop, I would say, right? And where we really see Ignite kind of excelling is when you really take advantage of it across a number of applications, right? And use it in what is called nowadays, very kind of popular coined term from Gartner, that HTAP, right? So hybrid transactional and analytical processing. So it's a system not that you can use it both for operational stuff, but also for analytical workloads, right? And that's where perhaps the SQL API provides the analytical side and the transactions API provides the other one. A couple of other things I think I want to mention of how the data is running or how it works within Ignite is we also support near caches, right? So we do support the server-side caching where you have a distributed hash map, but you can also create client-side near caching, right? Where you can operate on the client side. Now, that's also fully transactional, so you can commit and work with transactions on the client side on a near cache and still expect those to be consistent and committed to the database. When we talk about the key value API, that's fully JCache compliant, so it's aligned to the JCache specification. So if you're already using something with JCache, it's very easy to switch over, right, and use that. Okay, so I think bottom line is, I think we've got enough time, about 10 minutes to ask any questions, so I'll leave you with the main differences. So it's a new product. I think it's got a growing community. It's fun. I think there's a lot of new tickets and newbie tickets that you can start. So I think it's very interesting to get started and play around with it. So thank you, and I'll try and make it more interactive and take as many questions as possible.
Cool. Let's go ahead and give them a hand. All right. It's getting towards the end of the day. So,
yeah, I think everyone's going to rush for the beers, right?
A lot of technology. But does anybody have any questions?
I mean, if you can also spend some time in the booth, guys. We're going to be in the GridGain booth, so you want to catch up over a beer there, then happy to do that. But happy to talk with any of you or any questions go.
Hi. That's a good presentation, and I'm a bit confused. This works like a memory cache, a memory place where you mount your database you have on your storage. Like you have a SQL database, you mount that on memory center, and then you have access to that.
Yes.
There is a process that gets the data from the SQL, the storage, physical to the memory, right?
Yes.
Okay.
So you would call that the initial load. So how you do that, it's up to you, right? We can have an interface behind the scenes, which is called a cache store interface, and there you can integrate with any external data source, right? Whether being an Oracle database, a SQL database, but you need to define the contract of when I do a put or when I do a get in Ignite, what is the read and write through specification.
So it needs to be specifics, getting the data and spilling the data to disk too, right?
Yes.
From memory to the okay. Because it's a SQL interface, I can connect to Spark without using that RDDs Ignite, right?
Yeah, of course. I mean, you can connect as just a SQL database, right? You can use the JDBC driver and just treat it via JDBC or ODBC. Yeah, it's absolutely fine. Okay. Or you can use the Scala API to access it from Spark if you want to do that.
Now it's more clear to me how this works. Thank you.
Yep, thank you. Just one point to mention there, when you have an external data source, you don't have read and write through SQL, right? So you cannot execute a SQL query in Ignite memory and then expect that to also be forwarded to an external database. And hence, the introduction of the on-disk part actually solves that problem. So when we were working with a lot of customers, they're like, okay, memory is great, it's fast, but I have a lot of data. I'm not going to put all that into memory, right? It's not going to work. And when I have a separate system, the answer before was, okay, you have to preload it and then query it, right? And it's just not elegant and it's not going to work. But with the native persistence that you get, is you get that in one system. So you will have your hot data that's in memory and the historical data that's on disk. But when you issue a SQL query, that can also go through memory and also hit the disk parts. So, and that's one of the biggest, I think, changes that we're offering, with always keeping in mind that it's a memory-first system. So it's not a database that's just kind of added a caching layer. It's right the other way around. We just use disk for durability and recoverability, right, and historical data. Yeah, go ahead.
Just a quick follow on the earlier question. So when you're loading from the data store, keeps the same schema, or do you have to do some kind of mapping to?
It's entirely up to you. So for example, if we use a JDBC compliant database, we have a tool which comes with the web console that connects to your database, extracts all the table names and specifications, and then creates the relevant POJOs or XMLs that will work with Ignite. So then you have a one-to-one mapping. So it would be very easy to start and deploy Ignite as a cache on top of your database and do it automatically. We have also support for Cassandra, MongoDB, and some other stuff that's out of the box. But if you want to do your custom one, you need to define, right, what that contract is and how it's going to work. Interface.
All right. I think with that, we'll close out that first day. Let's give her another round of applause.
Thank you.